Okay. Well, at least we have half a class. Okay. So way back in Cal 2, we learned about really what enables you to do any integrals that you did in that class and in this one, the fundamental theorem of calculus that definite integral of some derivative, because you go back to the original function. Okay. Now, today we're going to see a similar theorem. Because we've learned how to do line integrals the last couple lectures. The line integral of a vector field, line integral of a scalar value function. But now we're going to see in certain cases anyway, there could be a much easier way to do that. Okay. Now, so to generalize this to, in fact, we're going to see a lot of theorems in this chapter that in some way are generalizations of a fundamental theorem of calculus, but we go to curves today, because here we're just integrating over an interval in one dimension, so it's just a line, or line segment. Today we're going to see how to integrate over a curve, and then later on we'll move up to two-dimensional and then three-dimensional domains. So suppose you have a vector field that is equal to the gradient, so the big F is a gradient of some function little f. So in other words, if I write f as having components, like I did last time, p, q, r, that are all functions of x, y, z, then this is equal to the gradient of f, meaning that little f x is p, little f y is q, little f z is equal to r. Okay. So these two statements are saying the same thing, it's just that here we're doing this on a component by component level. So if that's the case, then if I were to compute the kind of line integral that we saw last time of this vector field, so we're dealing with a line integral over some curve C, where, as always, C has parametric equations defined by some vector-valued function r of t, then if I follow the same procedure as before, and again, t is assumed to be between a and b, then I get the integral with respect to t from a to b, and so the usual formula from last time would call for this. All right. Now, if I were to write this as, so as usual, our parametric equations have components x of t, y of t, z of t. So if I were to fill in what I have about f and r on a component by component basis, what I have is my first component, so this is p, q, r, dot product with my tangent vector, x prime of t, y prime of t, z prime of t. And I didn't want to bother writing it out because it would take too much space, but p, q, and r all have x of t, y of t, z of t filled in. So, but the thing is, now I can say that p, q, and r are equal to fx, fy, and fz. So I can write this as partial of f with respect to x from P, and then I have dx dt. And remember, dot product is you multiply corresponding components and you add them all up. Something that you're going to be doing a lot of in this chapter. It's important to keep that in mind. And then I have q, which is partial of little f, these are all little f's, with respect to y, dy dt. And then r is, that's q, r is partial of f with respect to z, dz dt. So now my line integral becomes that. Now, this kind of expression, where I have these kind of partial derivatives multiplied together and added up, where have we seen that before? And don't tell me you haven't.
In the Jacobian.
What?
It looks more like a Jacobian to me.
Well, when you're multiplying Jacobians, but what's the actual?
It's like the chain rule.
It is the chain rule, yes. Yeah, where you're multiplying Jacobians. So, so really what we have here, this is the derivative with respect to t. So basically, if you're undoing the chain rule, it's a derivative with respect to t of little f with your parametric equations plugged in, dt. Okay. Because now if you think backwards, if I were to actually carry out this differentiation, what would I have? F is a function of x, y, and z. So I'd have to do df dx, dx dt, plus df dy, dy dt, and so on, and I'd get all this. Okay. But now, what that means is I have an integral of a derivative. So now I can go back to the regular fundamental theorem of calculus and work this out very easily. Okay. So what you get is just what's being differentiated, because the derivative and the integral are being canceled out. So you have f of r of t with limits a and b, and then you just go ahead and plug in. Then you just go ahead and plug in the limits. Okay. So, and now we're done. So to summarize, the fundamental theorem of line integrals says that if big F vector field is a gradient of some function little f, which I've discussed this a few sections ago, that we're saying the vector field F is conservative, also irrotational. Then the line integral over a given curve C of F is nothing more than little f, and little f in this case is called the potential function. Little f evaluated at the endpoints of the curve. Okay, in fact, what I'll do is I can write it this way: f of capital B minus f of capital A, where here's your curve C. So here's point A, big A, which is the parametric equations evaluated at t is little a, and then point B, which is parametric equations evaluated at the ending time, which is a little b. So the line integral only depends on the values of your potential functions at the endpoints. So what's interesting is it doesn't matter what curve it is, what happens in between those initial points. The work involved, because the value of the line integral can be interpreted as the work done to move an object along a curve, for a conservative vector field, the amount of work to get from point A to point B is the same, regardless of the path used to get there. So in fact, another term for this is, we can say the line integral is independent of path. Okay. Now, this makes things interesting in particular for the case where the curve C is a closed curve. So, suppose I have 2 points, so A and B. So I have one curve, I'll call C1, that goes in this direction from A to B. And then I have another curve that also goes from A to B, but using a different path. So I'll call this C2. Now, so under this assumption that f is conservative, so the line integral is independent of path, then the line integral of the vector field, let's see, over this curve, C1, will be the same as the line integral over C2, because they'll both be equal to little f at b minus little f of a. Now, from the curve C2, I could, let's see, okay, do some color chalk. If I were to trace this curve in the opposite direction, going from B to A. So what I'm doing in that case is I'm reversing the orientation of C2. So I'm going to call this minus C2. So minus C2 is C2 with the orientation reversed. Okay. So in fact, if I have parametric equations for C2 already, so C2 has parametric equations, I'll call it R2 of t, where t goes from A to B as usual. Then what I can do is I can define parametric equations for minus C2, and I'll call them, call it S2 of t. Well, the thing is, when I'm traversing a curve, I like to have my time values increasing. So if I'm going from here to here, I have my time values increasing from A to B. So what I could do in this case is I can say that S2 of t is equal to R2 of, say, B minus t. And I'll let t run from 0 to b minus a. Because then if I plug in t equals 0, I get point B. If I set t equal to b minus a, the b's will cancel and I'll get R2 of a. And I'm at what was the starting point, but it's now for minus C2, it's the ending point. And in many ways it's reverse orientation, but this is one convenient way to do that. And notice t now gives way to a minus t. So if I were to take the tangent vector of this curve and compare it to the tangent vector of this curve, they'd be negatives of one another because I'm traveling in the opposite direction. Okay, so orientation is important. So in general, the line integral over a curve C of a vector field is equal to, if you reverse the orientation, that negates the value of the line integral. That's only for vector fields. For the other line integral formula, for a scalar valued function, the orientation doesn't matter in that case because you have this square root expression, you have this magnitude. So the sign change isn't going to matter. But here, it does. So what I can say is, I can write this integral as an integral over minus c2 as long as I change the sign. Now, that seems pretty meaningless until I do a little rearranging. Because now I can take that line integral of minus c2 and move it to the other side. So I have integral over c1. Now I have plus the integral over minus c2 is 0. But let's take a look at this path that I'm traversing over c1 and minus c2. So if I redraw that over here, so I have point A, point B, so I'm going to pass C1, that's going in this direction, and then C2 starts from here, okay. So now what I have is, if I define C to be equal to C1 union minus C2, that forms a circuit, or what's referred to as a closed curve. And all that means mathematically is the initial point is equal to the terminal point. Okay. So for instance, if I define a circle, like x is cosine t and y is sine t, t goes from 0 to 2 pi, go around one full revolution. That's an example of a closed curve. So what we see here, and this is true in general, is if the vector field f is conservative, then the line integral of f along a curve C is always equal to 0 if C is a closed curve. So that's just a direct consequence of the line integral of f over any non-closed curve is independent of path. That it only depends on the values of a potential function at the starting and ending points. Okay. All right. Now, in fact, I can make this. So what it says, if f is conservative, the line integral is 0, because I can make a broader, stronger statement in that, and that is line integral of f is path independent, which would also mean that it's equal to 0 if C is closed. If and only if f is conservative. So you can almost take it to be a equivalent definition of being conservative. Okay.
What does it mean for f to be conservative?
Oh, just that it is a gradient of some function little f, which is a potential function. Okay. All right. Okay. Now, but the thing is, let's suppose we're dealing with a non-closed curve. So if you have this vector field that's conservative, and you have a closed curve, okay, you know the integral is 0, there's nothing to do. But suppose you have a curve that is not closed. What we see from the fundamental theorem of line integrals, from the statement here, if a vector field big F is what I'm given. But if I want the value of the integral, I need this function little f. So we say if big F is conservative, if big F is a gradient of some function little f, but that alone doesn't help me work out line integrals the easy way. Because if I want to do if I need to do a line integral to figure out work, for instance, I can do it the way I've already described to you, but that can be quite tedious. If we want this shortcut, there are two questions we need to answer about big F, and that is, how do we know that big F is conservative? How do we know that it's actually the gradient of some function little f? How do we know that some function little f that satisfies this even exists? And second question, if we know that that's true, what is it? We need to have a deterministic way of getting it. Okay. So what I'll do is so in 2 dimensions and 3 dimensions, how we can answer this question. And those of you who are taking or have taken DE 285, this might look familiar to you because it's similar to what you have to do to solve an exact equation. Doing a similar situation, you're trying to find some function whose partial derivatives are equal to given functions. So it turns out checking if big F is a gradient of something is actually quite simple. Okay, so especially the 2D case. Suppose big F is a gradient of little f, and big F has components, as usual, P and Q. So in other words, P is equal to Fx, Q is equal to Fy. Now, what I can do is I can take derivatives of both sides of these equations. I'll differentiate this one with respect to y. So I'll have Py is equal to Fxy. And then I can differentiate this equation with respect to x. So we're always using opposite variable. So I have Qx is equal to Fyx, but that's the same as Fxy. Again, we're assuming that everything's nice and continuous. So these partial derivatives, so that mixed second partial derivatives are equal. So because of this, we must have Py is equal to Qx. So that's how we can check. So given this vector field F, we'll just check these partial derivatives. If they don't match, game over. It's not conservative. If you need to do a line integral, it has to be done the hard way. Okay. All right. Now that's 2D. For 3D, your vector field has 3 components, P, Q, R, and you require that P is Fx, Q is Fy, R is Fz. So what you can do in this case is differentiate all 3 of these equations with respect to the other variables. So for instance, here I would say Py equals Fxy, Pz equals Fxz. And then similar over here, Qx equals Fyx, Qz equals Fyz, Rx equals Fzx, Ry equals FZY. So from here, I want to have a similar condition to this. Actually, I'm going to have 3 of them. So what has to match for this vector field to be the gradient of something? I'll start you off. This condition still applies. And you can see from checking here. Okay. But what else has to work? Okay, QZ equals what? RY. Okay. And? Yeah, PZ equals RX. Okay. So, so you can check those 3 things. And if they all check out, then great. It's a gradient of some vector field. The vector field is a gradient of some potential function, little f. Okay. So now I'll show you. Okay. Well, first I'll show you a general procedure for how to find little f in 2D, and then also show what to do. I'll give a 3D example. So So what you can do is you have a condition that dp dx must be df dx must be equal to p. So what I can do is I can basically take both sides of this equation and integrate it with respect to x. So I could say that f of xy, little f, is the integral of p of xy with respect to x. Now, here's where things get a little messy, because this is an indefinite integral. When you carry out an indefinite integral, like say if I have x squared, so I anti-differentiate that, I get x cubed over 3, but what am I missing?
C.
Plus c. But here we have functions of several variables, so it's a little more complicated than that. So let's suppose I carry out the integration, and I'll call the result, all right. Okay. So this integral I'll call f1. So in other words, what you have here, this is part of the little f you're looking for, but not the whole thing. And then you add something on. Now, you're accustomed to adding on this plus c. But really what you're going to add on is not a constant, but something that is independent of x, which means it's allowed to be a function of y. So you add on g of y. So this is what you used to know of as the constant of integration, but I shouldn't call it that because it's not a constant, obviously. But it is independent of x, and that's what matters. So then, that way, if I differentiate this with respect to x, this would go away. And then the derivative of this with respect to x would give me p. Okay. But the thing is, this, because I've integrated, I know what this is. I don't know what this is. So I still have to figure that out. Now, to figure that out, I need to use my other relationship. That partial of that little f with respect to y has to equal q. So here's what I can do. I can take what I know of to be my little f, So I'm going to solve this equation. Now I'm going to take this, differentiate it with respect to y, and set that equal to q. And I'm going to solve this for g. Okay. So in other words, I'm going to get this equation. G prime of y is equal to q, and I move this part over to the other side. So minus partial of f1 with respect to y. All right. So now what should happen here is both of these terms individually will depend on both x and y. But once I work all this out, simplify what I can, any dependence on x is supposed to disappear. If not, you did something wrong. Or maybe you're not really working with a conservative vector field. So I can figure out what this is. I'll get some function of only y, and then you just integrate. And in this case, everything depends on only y. So when you do integrate, there you actually do get a plus c. So your little f is never going to be determined completely, but it's always going to be some constant that you could add on. But any dependence on x and y is figured out. But then, after you do this, you're done. So you can figure out g, and then put that back in here, and now you have your little f. Okay.
Is that Q, X, Y?
Here?
No, down, that.
Yes. Let me get more Q-like. Okay.
Thank you.
All right. Now, this is 2D. If this had been 3D, I'd have little f of x, y, z is the integral of p of x, y, z. And then I would integrate, and I'd have g of y, z. Then I would go through this to narrow it down further. So basically, you keep knocking off one variable at a time until you have no variables left. And to illustrate that, I'm now going to do an example that's 3D. And yes, there will be a question like this in the final. And whether the given vector field is conservative. And if it is, find a function little f, whose gradient is your vector field. All right. So my vector field that has components p, q, r, all right, is 2xz plus y squared, 2xy plus just 2xy, and then x squared plus 3z squared. Okay, so this is p, q, r. Okay. Now, so first, we want to check to make sure it's conservative. So you need py is equal to qx, pz is equal to rx, qz is equal to ry. So if we go ahead and figure out these partial derivatives, well, what is dp dy? Oh, differentiate.
Okay, 2y.
Yeah. Okay, and qx. What?
With respect to
Yeah,
x.
2y. Yeah, differentiate with respect to x. Yeah. Okay. All right, pz. I think someone said it. 2x. Yeah, dp, but I say pz, I mean dp dz. Yeah, differentiate this with respect to z.
Oh, okay, I was looking wrong.
Okay. And then dr dx.
2x.
All right, so that checks out. And finally, dq dz and dr dy. Yeah, they're both 0. Okay, everything checks out. You know it's conservative. Okay, now we can start doing some integrating to figure out what f is.
So if one of those happen to not be equal, then it wouldn't be conservative at all.
Right, and then, yeah, all of them must work. Yeah. Okay. So now we can say little f, x, y, z would be the integral of p with respect to x. So if I integrate that with respect to x, so you're treating y and z as constants, what would you get?
X squared z plus y squared x.
Okay. And then what you add on is a function that is independent of x, but is allowed to depend on anything else you have. So I'll call that g of yz. That's unknown. Okay. So basically what you have is a template for little f, and you know part of it. Okay, so this comes from the fact that df dx must be equal to p. Now you use your second condition, that df dy must be equal to q. So I'm going to take a partial derivative of what I have so far, x squared z plus y squared x plus g, and set that equal to q, which is 2xy. So now if I differentiate this with respect to y, what will I get?
2y.
2y x.
2y
X.
x.
The x is a constant. And then this is unknown, but it does depend on y, so you have partial of g with respect to y. And that must equal 2xy. So what happens here is those cancel. So now you have gy of yz must be equal to 0. So what you could do at this point is you could integrate this with respect to y. Well, it's pretty trivial in this case. So, because if you integrate 0, okay, you get 0, but then you have your, whatever it is you need to add on. If I have a function of y and z, and I'm integrating it with respect to y, what would I add on? Function of only z. So I'll call that h of z, which again is unknown, just like this was originally unknown. Okay, so our unknown has been whittled down a little bit. We know that there's no y dependence. Okay, the last item is we use a condition df dz must be equal to r. So I'll differentiate with respect to z everything I have to this point. So I have x squared z plus y squared x plus h of z must be equal to r, which is x squared plus 3z squared. So now I sort this out. So if I differentiate this with respect to z, what do I have?
X squared plus h of z.
Not h of z, but h prime. Yeah. Of z. Yeah, so this gets differentiated too, and that must be equal to x squared plus 3z squared. The x squares cancel, because this should be an equation that has only z in it, and now it does. So now I have h of z equals 3z squared, h prime rather. So what is h of z?
DQ.
It's going to be z cubed, and here z was our only variable. So we integrated to get z cubed, and then you add on a plus c. Well, actually, I'm going to use k because I'm always using the letter c in this chapter to refer to curves. So now I can put this back up here, and now I know my g, so that really goes up here. So now I can say that my final answer of x, y, z is equal to x squared z plus y squared x plus z cubed plus some constant k. Any constant k will do. And then you're done. Any questions about how this played out? Now, having worked out many of these, I've noticed that another approach, and you might want to consider this, especially under time pressure for a test. Another way you could try this is if you were to take this and integrate in respect to x, this integrate in respect to y, and this integrate in respect to z, and knowing that all of these are supposed to equal the same thing after you add on any constants of integration, and if you get one function that satisfies all three of those, then you'd be done that way. In fact, if I were to do this, I integrate this with respect to x, and you get x squared z plus y squared x. Integrate this with respect to y, and you get xy squared. And then you integrate this with respect to z, and you get x squared z plus z cubed. And you notice all of them share terms. Now this z cubed is not anywhere else, but the thing is when you integrate these, there's this implied add-on. Like here you have a function of y and z. Here you have plus a function of x and z. Here a function of x and y. So if you can try to reconcile all of those, that's another way to get an answer. I didn't present it that way because this procedure is formal, it's guaranteed to work, but this is worth considering too. Because at least that gives you an idea as to what terms you're supposed to have. So in fact, you can think of this as your answer actually turns out to be the union of all of these terms. Now, dang it. Okay. So the last thing from okay, what I really want to present, I won't have time for it, but I do have one more add-on to this example. Now, let's suppose we have a curve C. And it has these parametric equations. So x of t is t squared, y of t is t plus 1, z of t is 2t minus 1, and t goes from 0 to 1. If we want to evaluate, so this I'm continuing what I have over here, so I still have the same f. So using the fundamental theorem of line integrals, we have that the line integral over this curve C of this vector field f, because it is conservative, is just going to be little f at my initial point, or sorry, my final point, which is r of 1, minus my potential function at my initial point, which is r of 0. Now, keep in mind, my potential function is x squared z plus xy squared plus z cubed. So all I have to do is get the initial and final points of this curve, and I can just plug them in here. So from these parametric equations, I can say the initial point at t equals 0. Well, what is the initial point?
C.
So I just plug in t equals 0 to my parametric equations.
-1.
Yep. Yeah, -1. Okay. Come on, people. I know you can do this. Participate. Terminal point. All I have to do now is plug in t equals 1 into the same parametric equations.
1,
Mhm.
2, and 1.
1, 2, and 1. All right, so this curve starts at this point, ends at this point. Okay. Now, I can just plug both of these into this function, x, y, z, x, y, z. So for my final point, I'm going to have, okay, so x is 1 squared times 1 plus, I'm following this formula here, xy squared, so that's 1, 2 squared plus 1 cubed. Minus, okay, because this is x squared z plus xy squared plus z cubed. So now I have this point, my initial point, to plug in. So that would be 0 squared times -1 plus 0 times 1 squared plus -1 cubed.
It's just going to be
Okay, and yeah, I had an arbitrary constant k, but that's just going to cancel out anyway, so I didn't even bother with it. So I have 1 plus 4 plus 1, so
4
6
plus 1.
minus a -1 is 7.
Oh, 4,
This worked out on page 119. So, so I'll be integrating, you actually did over there with respect to x, y, and z, to come up with a little f, but then you can just plug in the endpoints. So whatever happened on this curve in between turns out to be irrelevant. Okay. All right. Any questions about?
And what exactly is that 7 for? That's our
That
k?
is that's the value of the line integral of this vector field over any curve C that starts and ends at these points. So instead of working out like a parametric equations like last time, you can just do this. Any questions?
Well, we just used our f, x, y, and z from over there.
Yeah, to do.
And you gave us the initial.
Yeah, but the initial vector field big
Zero.
F is
Okay.
yeah.
But you gave us a new that c is.
Yeah, that's C is new right here. Yeah.
Yeah.
Yeah. Once you have little f worked out on whatever curve you're given, you can now do this if
Okay.
it's conservative.
So that's the first part, and that's the
Yeah.
second part
Yes.
after you do this.
Yes.
But you can't do that until you do it. And we didn't do the k, so after when you subtract it, it's going to cancel out. So it's going to be k
Yeah.
minus
Yeah.
k.
No point. Yeah.
Okay. That makes sense.